So here we get to our final class of carbonyl reactions, which is the alpha substitution. Now you may notice we have another chapter on carbonyl reactions coming up after this, but that next chapter, which deals with condensation reactions, it turns out a lot of condensation reactions are really just applications of carbonyl reactions that we've already learned. So this is the last chapter of carbonyls that really has a lot of new concepts in it. So what do we mean by alpha substitution? So first of all, either of the carbons that are adjacent to the carbonyl can be considered the alpha carbon. And we can name carbons as we go further away from the carbonyl, as beta and so on. But it's the alpha one that we're interested in most of all. And that's because that alpha carbon is acidic. How acidic is it? Well, something like the beta carbon, which is a pretty typical carbon, has a pKa of somewhere between 40 and 50. So, very high, not at all acidic, similar to most carbons. But the alpha carbons, the ones that are directly next to the carbonyl, have a pKa in the range of 18 to 20. And 18 to 20, if you think about that, is very similar to the acidity for an alcohol. So alpha carbons, much, much more acidic than your normal carbons. Now, why is that? Well, upon deprotonating the alpha carbon, and we could do this for either of the two positions, we'll choose this one right now. But upon deprotonation, we form an enolate. And our enolate can delocalize that negative charge into the carbonyl. And then that enolate, if we add acid into it, will form an enol. The ketone and enol forms are known as tautomers, which means that they are rapidly equilibrating constitutional isomers. And specifically, you can do this under acidic or under basic conditions. Now, be careful, because we want to say that the ketone and the enol, these are tautomers. They're constitutional isomers. They are not resonance structures. Why are they not resonance structures? Because we've taken a hydrogen and actually moved its location. So we've broken a sigma bond here, and we've formed a new sigma bond for that OH group. Now, as I said, we can do this under either acidic or basic conditions. The reactions are relatively similar. Main difference is the order of the steps. We've seen plenty of carbonyls reacting under acidic conditions at this point to know that the first step is going to be protonation of the carbonyl. Why do we need to protonate under acidic conditions? Well, under acidic conditions, the alpha carbon is going to need some help in being deprotonated because we don't have as strong a base present. About the strongest base we're going to have is water. And so water, not a good enough base on its own to deprotonate the alpha carbon of the carbonyl, but once you protonate it, once you activate it, makes it more reactive. Water can remove that hydrogen, and we form our enol. Under basic conditions, essentially these two steps are reversed. Because under basic conditions, we can have a much stronger base, such as hydroxide or something stronger, which can remove the alpha hydrogen and directly form the enolate. then that enolate can grab a proton from water and also get us to the enol. Now, due to stability, regardless of your reaction conditions, acidic or basic, in almost every case, the carbonyl form is favored over the enol. And in a case like acetone, under acidic or basic conditions, it's a pretty strong preference. But in some special cases, you can have compounds where the enol is favored. Probably the most common situation is if you're dealing with a dicarbonyl. In the case of a dicarbonyl, if you form one of the enols, that OH group can form an internal hydrogen bond with the other carbonyl. And that internal hydrogen bond is able to stabilize the enol. And while you're not going to get as strong an equilibrium as, say, in the acetone case, you still, by a ratio of almost 3 to 1, get preference for the enol for one of the carbonyls over the carbonyl itself.